Relation between generalized harmonic number and polygon function. I guess you guys know about both of these terms. If you don't know, like let me just share about it. So generalized harmonic number basically is defined by the following expression. Harmonic number, kth harmonic number to the order of p is defined as sum from n equals to 1 to k of 1 by n to the power p. So basically all of these terms are raised to the power of p, yeah, in the denominator. And if it's up to infinity, this actually becomes Riemann zeta of p. Okay, now fine. And polygon function is basically, we know that the digamma function, of let's say g plus 1, this is defined as negative of Euler-Masonry constant plus sum from, or let's say we have gth harmonic number. This is actually the definition of the digamma function, and we know that gth harmonic number can be written as negative Euler-Masonry constant plus sum going from k equals to 1 to infinity 1 by k minus 1 by k plus c. Yeah. Now if we go on differentiating this, the first derivative is known as trigamma function denoted as digamma 1, and then quad gamma function denoted as digamma base 2. Yeah. And it goes on, and basically if we have p minus 1th derivative is there, polygamma function are basically just the derivatives of digamma function. Yeah. Now let's try to find the p minus 1th derivative of the digamma function, and let's see how can we relate the expression that we get with the generalized harmonic number. If we take the derivative of this expression with respect to g, the first derivative, so since the constant is just a constant, if we differentiate it goes to 0. Over here also, since the derivative with respect to g, 1 by k is just constant, and over here we need to do the derivative. We have sum from k equals to 1 to infinity. This will just be 1 by k plus g whole square. Yeah. Next, if you again differentiate this expression, we have this digamma base 2 of g of 1. This basically represents the second derivative. Over here we basically have negative 2 sum from k equals to 1 to infinity of 1 by k plus g to the power 3. Yeah, we can differentiate this easily. Minus 2 comes in front. Yeah, this is from the power rule of differentiation. Again, if we differentiate this, again now we get the negative 3 outside, so that means now 3 times 2 is basically just 3 factorial. Sum from k equals to 1 to infinity, k equals to 1 to infinity 1 by k plus g to the power 4. Similarly, if you go on, if we try to find fourth derivative of digamma function, you basically now get negative of a factorial, and then sum from k equals to 1 to infinity of 1 by k plus g to the power 5. Yeah, and this can go on, and notice that if we have a power p, basically this sign, negative sign, is basically whenever there's even, there's no negative sign, whenever there's odd, there's negative sign. Yeah, so do notice that, and from that observation we can like generalize this expression. If we have sum from k equals to 1 to infinity for 1 by k plus g to the power p. Yeah, the sign over here is also governed by that p mentioned to the power p, and over here we have p minus 1 factorial. Yeah, and this is equals to, basically it is also 1 less than the p, so p minus 1th derivative of digamma function times g plus 1. Yeah, so this is what we have got till now. Now we need to relate this with the our generalized harmonic number. So how we can do that? So let me share how we can do that. So basically what we can do is we can uh, manipulate that sum. We can manipulate that sum in the following way. The way is, so this sum basically goes from g plus 1 to infinity. Yeah, so what we do is we introduce this sum where basically all the g's are included. Yeah, this goes from z plus 1 to infinity. This goes from 1 to infinity. We will subtract from 1 to z. From k equals to 1 to z of 1 by k to the power p. I'm sorry, this one is actually k to the power p, not g to the power p. This one is actually k to the power p. Yeah, this goes from 1 to infinity. This goes from 1 to z. So remaining is from z plus 1 to infinity. Yeah, so that makes sense. Now let's take it to the divide. Minus 1 to the power p minus 1 derivative of di gamma function divided by p minus 1 factorial. Yeah, and over here we know that this sum is just the Riemann zeta of p minus, and this one is over here is just the harmonic number of order p. So we can write this as, since it goes up to z, this is just zth harmonic number of the order p. Yeah, and so now we are almost there. And if we try to isolate the zth harmonic number, what we get is zth harmonic number to the order p is Riemann zeta of p. Now if we take this to the other side, the minus sign will basically change to minus 1 to the power p minus 1, yeah, because here's an additional minus 1. And then di gamma p minus 1 derivative z plus 1 by p minus 1 factorial. And you can see that now we have the relationship between the zth harmonic number and the poly gamma function. Let's check if this relation is correct or not. If this relation is correct or not. If there was k, there would be k plus 1. Yeah. And sk of order p is equals to zeta of p plus minus 1 to the power p minus 1 poly gamma p minus 1 k plus 1 by p minus 1 factorial. Yeah, that's the relation. We know that just to make a like complete solution, we can write this as this is just the sum from n equals to 1 to z of 1 by n to the power p. So that concludes the solution. Talk about the flow. We just took the derivatives of di gamma function and like noticed the patterns and like divided the sum, and that gave us the answer. Thanks for watching. Hope it helped you to learn something new, and hope it was helpful. And look forward to seeing you in the upcoming videos too.